Proving trigonometric identities, one of the coolest things you can do. This is taking algebra to a whole new extreme because guess what? We're going to throw some trigonometric identities in there, and oh my goodness, this ought to be a blast. One of the things that you have to keep in mind, the ultimate goal here is to prove an identity. You must show that the left-hand side of the equation equals to the right-hand side of the equation. And cool thing is when you graph this, remember, you could put this down as y1, y2. If you do that, let's say your y1 looks something like, I don't know, like that. Then your y2 will put the exact same graph right over top. If it is out even the slightest, that means it's not an identity. Identity means left side equals right side. So in this case, y1 is going to equal to y2. So that's the in on graphing. But how do you do this algebraically? Well, algebraically, you're going to manipulate things. You're going to manipulate each side algebraically using identities that are on the worksheet that you have, those identities that are on your formula sheet. So what are some strategies on how to do this? Well, surprisingly enough, you're going to start with the more complex side. You're probably looking at it and go, what? What are you talking about? Yeah. Usually, if you're starting with the more complex side, that means something that can be canceled. Something's canceled, something can be reduced, something's going on there. Why is it so complex? Take the complex side, make it more simple. Now, here's another thing. Watch out for key identities, like the Pythagorean identities. These are the ones that are the squares. Look for those. As soon as they show up, you know that you can start playing around with them. And remember, you can rearrange things like sine squared x plus cos squared x equals to 1. You can rearrange this guy. So it looks like, well, remember, you can have 1 minus cos squared x. That'll give you your sine squared x. Or you can have 1 minus sine squared x equals to cos squared x. You can manipulate this. Don't forget, you're not just stuck using this guy the way it looks. Okay, next, what's another strategy? Sometimes putting everything down in terms of sine or cosine is probably the easiest way to do things, because then you can go, you can actually cancel sines or you can cancel cosines, and you don't have to worry about, gee, what does this mean? Is it the cotangent one sine over cosine, or is it the tangent one, or is it the secant one? You don't know. So you look at this and go, okay, just break it down into sine and cosine, make it simple, and away you go. Another thing to look for, factoring. Yeah, if you can factor it either PSA, difference of squares, or any other kind of factor, you'd be surprised it works out great. Watch out for the sum and difference of fractions, okay? When you get these guys, maybe you might want to put them together as a whole fraction. Look for common denominators. That's another one. And one of my favorite is conjugates. When you look at the conjugates, what's really, really cool about this comes from the difference of squares idea. Do you remember this, where we had 1 plus root 3? And how we got rid of this is we multiply it by 1 minus root 3. And that's because that middle term cancels when you FOIL. Yeah, remember this? That gives you 1, that gives you minus root 3 plus root 3, and those guys cancel. And check this out. When you go root 3 times minus root 3, that becomes minus 3. And look how this works out. Oh my goodness, that's going back to Math 20. You can do the same thing, surprisingly, with sines and cosines, and things work out really, really well. Okay, couple important points there. You have to have a flow in your proof. You can't just jump steps and assume everybody to know what you're doing. Okay? Also, don't move the terms from side to side. Solve the left-hand side, then separately solve the right-hand side, and then figure out if they equal. There's no such thing as cross multiplication either. Sorry, I know you want to do this, but if you do that, you're combining sides. You can't do that. Each side has to be solved independently, okay? All right? And there's the thing I just talked about in terms of conjugates. Conjugates, again, based on the difference of squares. This could be one of the most powerful things you can do. Remember, 1 plus cos x, the conjugate is 1 minus cos x. Secant minus 1, the conjugate, secant plus 1. That's going to come into play coming up really, really quick. Okay, so pitter patter. Let's get at her. Oh my goodness, look at this monster. Well, probably the first thing that you can do here is read the question. It says, consider this identity. So they tell you this is what you're going to be working with right here. Look how ugly that is. It's a monster. But the thing is, it says, verify the identity numerically under x equals to pi over 6. Well, what does that mean? Wherever you get an x, put in a pi over 6. So this is 1 minus sine squared. There, put the pi over 6 in there. Boy, that's really tough. Giving you sine squared pi over 6 again, but this time you're multiplying it by the cotangent squared of pi over 6. And I know what you're saying. Oh my God, how can you keep this all straight? It's actually pretty easy to keep it all straight because you got to remember, hey, wait a second. What is pi over 6? What is the sine of pi over 6? So pi over 6, is this guy. The sine of pi over 6, this is root 3 over 2. This is 1/2. So the sine of pi over 6 is 1/2. So this is 1 minus a half squared. Oh, that wasn't so different. This equals 2. Oh, yeah, you guessed it. Think about it. Sine squared again. So this is going to be, guess what? 1/2 squared again. But this time you're going to multiply it by cotangent. There's where the little play on things might come in. Think about this. What is cotangent? Cotangent squared is, if you think about it, this is the cosine squared over the sine squared. That's why I wrote out this point the way I did, because I wanted to see the cosine. Now think about this. This would then be multiplied by, okay, what's cosine? Cosine is root 3 over 2. We're going to square it. Over the sine squared, which is 1/2, we're going to square it. Look at this. When we square this guy on top, don't we actually get 3 over 4? Yeah, no kidding. This guy here means to divide. So we're dividing by the square of a half, which is a quarter. You know and I know, you take this guy, take the reciprocal, and look what we got. We got an answer of 3. So what do we have here? Cotangent squared then is just plain old 3. Oh my goodness, that's really tough. Now, the cool thing about that then, let's keep on going, is this. Watch this. 1 minus a half squared is like saying 1 minus a quarter. Notice how I'm doing left side, right side. I'm bouncing back between the two, but I'm keeping them separate. This is 4 over 4. So 4 over 4 minus a quarter works out to be 3 over 4. How delightful. Okay. Now, this is squared. So isn't this a quarter times 3? Oh, look what I got. Oh my goodness, I get 3 over 4. So far, that identity says it works. But remember, this is only working right now for one thing. That's all it's working for. You've proved it for pi over 6. Doesn't mean all of them are that way. You got to prove this for everything out there. Okay, so what I would do is I would look at this and go, okay, let's try to see if we can do this graphically then. Well, think about it. How would you do this graphically? Well, easy peasy. What I would do is I would take this guy. Let's clean it up a little bit so I can actually see it. There it is. I would take this guy right here, make it y1. Take this guy right here, make it y2. Well, why don't we do this right now? Now, remember, you're dealing with radians here, so make sure your calculator is in radians. Set your calculator up so it has a window from 0 to 2 pi. I don't know what to put the top and bottom mins at, so I'm going to put maybe, 3 and minus 3. That's good enough. That should work and show us a nice enough of a graph. And then let's just go out and put these guys in here. Okay, so I've set the calculator up. I'm already in radians, as you can see in my display right here. I'm already in radians, so everything's cool. Let's go out and solve this, shall we? Okay, so let's put in y1. Do you remember what y1 was? Sure, it's 1 minus. Now, remember, the sine squared is squared. So how do you do this? Simple. You got to put this in as sine x. And notice, look how many brackets you have here. You actually have 4 brackets to deal with. You have 4 brackets to deal with because you're taking the entire sine and squaring it. That's what you have to do in order to put down sine squared. Kind of crazy, isn't it? Yeah, design me another calculator that does it nicely like the way we normally write it. I would be appreciative. Okay, now, next one. Remember, this was sine squared. So again, you got to do that crazy bracket stuff. Okay, watch how many brackets you're going to have. All right, that's important. There's sine squared. And remember, this was multiplied by cotangent squared. Oh, man, how do you do cotangent? Well, remember, cotangent is 1 over 10. So here we go. Alpha, there we go. There's our fraction, 1 over 10. So that you got to do it that way, unfortunately, because guess what? Yeah, you know what? This beautiful calculator does not do the secondary trigonometric ratios. So you got to do it that way. And of course, this is squared. So what are you going to see? You're going to see a blue line drawn first, and then hopefully right over top, the red line. Okay, keep your fingers crossed. Drum roll, please. Brrr, bing. And oh my goodness, look at that. What does that mean? The graphs are right on top of each other. That must mean y1 equals to y2, which eventually means, yup, this equals to that. It is an identity. Now, here's the cool thing. Here's the real cool thing. What we want to do next is we want to say, okay, let's look at a couple things. Okay, let's look at C. C says here, determine the values of x which the identity is defined. So in other words, find me the non-permissible values. The only problem that's an issue here on the non-permissible values, if you think about it, is this guy. Everything else, they're all numerators. Cotangent is the only denominator. Yup, right there. There's the denominator in terms of a sine function. So you got to put down sine squared theta cannot equal 0. Square root, you find out that sine theta, we would normally put down plus or minus, but we don't have a plus or minus 0. So we just said sine cannot equal to 0. That's what defines this. You cannot have a sign that's 0. Okay, now, finally, let's go and prove this algebraically. Okay, so first things first. I'm going to write this down again. 1 sine squared x equals to sine squared x cotangent squared x. Where do I start? Well, there's a couple things we can do. I don't know about you, but it's hitting me like a 2x4 right between my eyeballs. Okay? Look at this. Is that not a Pythagorean identity? What are you talking about here, sir? Well, let me show you. Watch this. If I solve this guy, if I rearrange this, isn't cos squared x equal to 1 minus sine squared x? Isn't it? Of course it is. So guess what? I can replace this guy. How can I replace him? I replace him by calling him, oh, look at this, cos squared x. That's it. Now, once I've gotten down to something as simple as that, I can't do anything else. I'm done with that one. So now let's start looking at the right-hand side. Well, there's not much I can do with this guy. That, of course, is sine squared x. But can I play around with the cotangent? Oh, you betcha I can, because you know and I know that cotangent squared is actually cos squared x over sine squared x. Beautiful. Beautiful. Look what cancels. Broop, broop, it's gone, leaving you, look at this, cos squared x, the left-hand side, equals to cos squared x on the right-hand side. Now, that means the identity, it's down to its simplest form. It is proved. So instead of putting a check mark down, the way really cool mathematicians do it is we put a little square at the bottom of this and we shade it. And that little shaded square, it says, we're done proving. And that's the proof that that identity works. Stay tuned for more.